Okay, we got it. So yes, we have formative assessment number 5 to talk about. I went through all of your answers and updated grades this morning. So if you've turned in any work since about 9:50, it's not included, but if it's up till that point, you should have your current scores on the landing page. If you think that there's anything that's incorrect or that I missed, please let me know. I still haven't fixed question 66 from the previous homework yet. That's on my to-do list. I will do it at some point. And so you don't have to worry about that. But for now, we have a few questions to discuss. So what does it mean to have dependency? What did you write down?
Correlated residuals.
Correlated residuals, that's the big one. And so in reading what folks wrote, I realized that there's somewhat of a semantic distinction as to whether the correlated residuals are within one variable versus multiple variables. So a few people wrote things like, if you have somebody take a pre-test and a post-test, those two sets of scores would be correlated. And I agree with that. And I wouldn't think of it necessarily as an instance of dependency, though, because they're two separate variables and two separate columns. But if you were thinking of it as just score in one column, then the idea that two scores come from one person would create dependency. So that's what I mean by it's somewhat of a semantic distinction as to whether you're talking about one variable or multiple variables. Most of the time, if you're thinking about it as separate variables, then it's an obvious case that you would need to address the relationship between those variables in a model, either by making one a predictor and one an outcome, or multiple outcomes, or something like that. But the more insidious case is when you don't necessarily expect dependency because you're thinking of it as one thing. So for instance, if I take math scores of all the children in Iowa City, I might think of that as math score. But there's sources of dependency within math score because of the way the children are grouped, either within classrooms, teachers, units, schools, districts, and so forth. So I was going for more of that sort of situation where it's not obvious that you would have to think about it, because people who haven't had coursework in, say, random effects models might not think that way. They're still thinking about scores and children as the unit of analysis, but you would have to address dependency somehow in that type of situation. What else? What else did you write down for this one? Had some good examples. Kaylin, can I call on you? What was your example?
My example was just kind of your example. My previous program was is human development and family science also. So that idea of like studying family members, especially when studying family members in relation to like different models and trying to find out if like different models are effective for different treatments and stuff like that, that creates dependency just because the family members are going to have residuals that are always correlated with each other.
Mm-hmm. Yeah, they have common experiences, common genetics in some cases, common factors. There's also, like, if you think about national longitudinal data sets of children that are available, sometimes they sample multiple siblings from the same family. So that would be another instance where dependency is something you don't necessarily jump to right away, but if you think about it, yeah, probably if you have two kids from the same family, they're going to be related, particularly if they're twins. And interestingly, the models that people use to try and carve up variance in twin studies as to how much is genetics versus environment, all of that is based on the correlation between twins. And the idea that twins that are identical or monozygotic should have a higher correlation, and twins that are dizygotic should have a lower correlation. And the difference between the correlations is used to carve up the genetic component versus the environment component. So dependency.
Does that come from those twin studies that were done in like the 70s or 80s, or are they different studies that they're looking at?
Like, it's still an active area of research. I have papers within the last couple of years that have been published on twin stuff.
I think I'm going to email you about that because that's really interesting.
Sure. The short answer is that heritability is twice the difference in intraclass correlation between MZ and DZ twins. So once again, everything is a mixed model. Everything. All right. I think I've beaten that one to death. Any other questions or comments on number 1 here about dependency? Correlated residuals within an outcome. That's the big picture. All right. Balanced and unbalanced. This one, everybody has the big idea for. This is my terminology. Other people might use these words a little bit differently, but this is how I think about it and how I've read other people using these same words in the same way. Balanced is the idea that there's a common set of possible outcomes, and unbalanced means there's not. And I had a couple questions about this from folks who were answering the question, does this have to do with how the fixed effects are specified? And the answer is no. You can put in whatever predictors you want. Like the only thing that is limiting you is your creativity and what's in the data set. So that's not a concern. The issue is, what are your choices for capturing the dependency across multiple outcomes from the same sampling unit? There are fewer choices if your data are unbalanced. So the balanced outcome case, you have path models, you have, the mixed, or what do you call it, the direct, just add the correlations in. You can do that in path models as well. For unbalanced outcomes, random effects are pretty much the only way of introducing correlation. There's one class of correlated residuals that's known as a first-order autoregressive model that can be extended to at unequidistant time occasions, so times that are vary across people, but that's the only one that I know of. So it's a strategy distinction as opposed as for what you can do with respect to the variances and covariances, not a strategy decision with what you can do with predictors. And we're doing balanced in this class. And if you want to do unbalanced, come to a different class. So there's two different multi-level modeling classes offered in our department. There's also longitudinal models offered in the statistics department. And I want to say that there is a mixed models class in psychology, maybe too. So there's multiple places that you can get treatment of these sorts of issues and multiple ways of describing the same types of problems. All right, any more on that one? Okay. Question 3. So in situations in which you could estimate a separate model for each separate outcome, what are some advantages from not doing that and doing a simultaneous analysis predicting multiple outcomes? So there's lots of possibilities here. What do you think? Let's start listing them all. Why might we want to do this simultaneously? What can you learn from putting things in the same model for multiple outcomes that you can't learn as easily or at all from doing it as separate? Different predictor effects. So yeah, if a predictor has a stronger effect on one outcome than another, that either presupposes that they're on the same scale or that you're working with the effect size rather than the slope. So if you have outcomes that are on different scales, your predictors will have different slopes for that reason alone. So you'd have to correct for that somehow, either by standardizing the variables or working in a standardized metric somehow. But assuming that they share a common scale. Yeah, different predictor effects is one. What about power? A few people reference power in their answers. I didn't talk about this a lot, but it's true. You may have heard about it from other classes. How does analysis strategy with respect to separate versus simultaneous models affect power potentially? No ideas? Okay, well, let me give you a few. Let's say that you test differences in predictor effects and you don't find any. That basically you can fit one slope that predicts two things. Fitting that one slope will have more power than fitting two slopes. Generally speaking, the fewer parameters you can get away with, the better estimated each one will be. Another is in the case of missing data. So if you have an outcome that has missing data on it, to the extent that it's correlated with another outcome, then they sort of borrow information from each other, and you can end up with more powerful effects because of that borrowing type of process. So that's one reason. What about mediation kinds of stuff? We haven't talked about that yet, but you've probably heard that term. The idea that X causes M and M causes Y, and there's potentially multiple X's, multiple M's, multiple Y's. It is possible to answer questions about mediation in separate piecemeal regressions, but it's kind of clunky, and it becomes overwhelming once you get a model of any sort of level of complexity. What else? I have a few more in my head, but looking for the participation angle here. Normally I'd say, feel free to read from the slide, but this isn't a slide. It's just a blank box. What about relations between your outcomes? Might you want to know if they're related to each other? If how well you do in one condition is related to how well you do in a different condition? Sure. Those sorts of correlations between outcomes are sometimes of interest. They become residual correlations after you control for fixed effects. But that's something else that you might be interested in that you wouldn't get from separate models. Anything else come to mind?
Yeah, I think that you mentioned that we could explore differences in the outcomes using different link functions to the different models that we can use, for example, in path analysis.
Mm-hmm.
And that's useful, and we do not have to assume for the different outcomes, for example, the same stretch factor, mm-hmm. something that we cannot use in the direct approach.
So the idea of choosing different link functions for different outcomes?
Yes.
Is that what you're talking about? Yeah. Yeah. You could do that in either case. It's trickier to do if you're tricking univariate software. It's easier to do in a path model framework where everything is treated separately in its own column. But yeah, that's an advantage of I would say, the path model version of the multivariate model.
And I have a question. So, mm-hmm. if we do not have to use, or if we do not have to assume the multivariate normal distribution for the conditional distribution,
yes.
And if we can use different link functions to different parts of the path model, can we use different conditional distributions, or can we assume different conditional distributions for the residuals?
Yes. Okay. Yes. So did you hear the question, Zoomers? Okay. The question was basically, you can choose different link functions for different outcomes in path analysis. Can you choose different distributions? Yes, to the extent the software lets you. That's the limiting factor, is what's available in software. So for instance, Lavon, to the best of my knowledge, has cumulative logit, and that's it. So you can't do like count models and stuff like that as a path model in Lavon. M+ has Poisson, negative binomial. Both of those are zero inflated. It has hurdles, two-part nominal, ordinal, and it added adjacent categories. So it has the most out of any of the packages that I'm familiar with. Stata's GSEM has quite a few as well. They have a lot of options for that. The tricky part with when you start bringing in the generalized aspect to the multivariate model is that you have to use latent factors / random effects to induce the correlation between outcomes, because you can't just let them be correlated. A direct correlation between outcomes that are not normal is not allowed. So there's a workaround that I'll show you in our very last example, that by adding a random factor that does the same thing. That's the trickier part. Okay. Anything else on that point? Questions or comments? And then last one, relevant to the example we're working through in your homework. How does the parameterization of fixed effects change? So parameterization is a fancy word that means how I set up the model. This is a choice. And by the end of this class, I'll be honest with you, my goal in teaching you this semester has only been a little bit about generalized models. It's been about drilling the crap out of you with linear models. By the end of this class, you will know how to do anything that you want to do out of a linear model. How to rearrange it, how to get whatever fixed effects, linear combinations of fixed effects, differences in fixed effects. You've all gotten really good at that. So that will serve you well in all of your future coursework and models, because linear models run the world. So expanding your toolbox of how you can set up a model to give you what you want. There is sort of the general intercept version that we talked about versus outcome specific. So what's the difference? And when would you want to do each, maybe? And if this is still fuzzy in your head, that's totally expected because we just started talking about this. So first up, let's just define them. General intercept version is when you have a column of ones that applies to every single case in the database. So it is the expected outcome, that fixed general intercept is the expected outcome when all the predictors are 0. So that's the way that we're used to seeing a linear model. And then every other fixed slope represents a deviation from that single general column. So the fixed slopes that you would put in for which outcome is which would then represent mean differences between outcomes and conditional mean differences between outcomes once other predictors are included. That's one way to set up the model. The other way is to shut off that common column of ones and create your own that's outcome specific. So it would be like a column of zeros and ones and zeros and ones, where each one acts like a switch that controls when the fixed effects apply to each row. That's the DV specific or outcome specific intercepts version. So that's what we're looking at, starting to look at in example 5a, and I will give you some pointers on your homework related to that as well. So when would each be more useful? What do you think?
I think that when we are interested in the comparison between different conditions, we can use the general intercept version. But when we have some kind of clue or hint about the differences between the categories of our dependent variable, we can use different intercept or a specific intercept for each group, and then get the differences using linear comparisons between them.
Yeah, I think that's a good way of setting it. Yeah, if you're interested in the differences between your DVs or your conditions specifically, a general intercept version gives you that exactly. But the problem is that then all of your predictor slopes pertain to a reference DV, and then you get the difference in the slope for the others. So to get what it is for each subsequent outcome, that's a linear combination. Whereas shutting off the general intercept, turning on the specific intercepts instead, then you get the prediction for each outcome specifically, and the linear combinations you would need would be for the differences. So you get the same information at the end of the day in both cases. It's just which comes directly from the model and which you have to ask for separately. And that might be a good segue into our example. So we can look at numbers because it makes it easier to understand once you look at code and numbers sometimes as opposed to general concepts. Okay, any questions on that or any of the others? Okay. And by the way, if you have questions and they come to you when you're not sitting in class, like if you're watching the videos or something, feel free to shoot me an email. Just be like, hey, can we talk about this on Thursday? I'd be happy to entertain spontaneous review questions. Then I will shut this one down, and we will look at, we are going to go to, let's do example 5a. We just got into the data part of this, and I think maybe a couple empty models. Does that sound right?
Yep.
Yep, okay. So this is example 5a. By the way, I'm waiting to see how much time we actually have for the material that I have planned, because as usual, I have planned too much material. So I'm going to have to get picky about what I'm going to present and what I'm not going to present. That's why I haven't updated the website yet, because I'm waiting to see how long this stuff takes. If nothing else, I can put up links to videos and materials from the last time I taught this class. I just won't have R in that case. So it's just SAS and Stata. But anywho, these are real data collected from a study that was at Penn State University when I was a postdoc there. We have marital attitudes about gender roles from an adult child, their mother, and their father. So 3 people as the repeated measures. So the unit of analysis here is the family. That's what I'm thinking of it. This is a family level study. It's multivariate because each family is measured 3 times. 3 different members are the outcomes in the story. And the outcome itself is a scale score, because this is not the structural equation models class, in which Higher scores mean more conservative attitudes, and it's from a range of 1 to 4 because it's the mean across items of a Likert scale. We're only going to have 2 conceptual predictors, the gender of the adult child and the education level of each person, such that 0 is high school degree. So the first thing that we have to do this analysis, if you're trying to use univariate software, which we are in part 1, part 2 we'll do this as a path model, is to restructure the data so that there's only one column that holds all 3 outcomes. So that is what's known as stacking the data. It's also known as reshaping. So those are the words that you should ask the Google for if you're looking for how to do this in a given program. And it's the idea of transposing by row a data set where a row is per family and turning that into a data set where a row is per outcome per family. So in this context, each family on the bottom here has 3 rows of data where I have the original variables that were in here. I have a new categorical identification variable, which is whether it's the kid, the mom, or the dad. And then these 3 dummy codes, which are going to work as our DV-specific intercepts in the example. And then here is the column that holds all 3 people's marital attitudes. Okay, question?
Yeah, if we would be using, for example, different outcomes for a single person. In this case, the family ID variable would be time variable, and
Yes.
DB would be the X predictor that we should have to introduce in the model as linear predictor.
So the X predictors are over here. These 4 columns are going to be the X's. This
Okay.
DV is an identification variable. So it's treated as categorical in the model. It's used to structure the R matrix. And then these are the DB-specific intercepts that we're going to work with.
Okay.
So I don't think of them as X's in the same way because they don't hold any information other than which outcome it happens to be.
Okay, because I remember that you said when we have a single outcome, we can use an X variable as a predictor in order to switch off or switch on different times.
Yeah, it's a semantic distinction, but to me it's like this isn't really a predictor.
Okay.
I think of it as a switch. If you want to call it time, then I might call that a predictor, even though that completely is internally inconsistent. But the role of this, what the purpose of these variables is to control which fixed effects are going to predict which rows. And note that the way that this is structured, and I've made this a deliberate choice, and I'll explain why when we get through the models, is that I did not create a column for education that looks like marital attitudes. I could have. I could have created an X column where I have each person's education level per row in the same way that I have each person's outcome per row. And I did not do that. In short, the reason is because I want to see how, like, the dad's education predicts the kid's outcome and how the mom's education predicts the kid's outcome. And if I had stacked it into one column, I couldn't do that. So if you keep the data in this format, where every potential predictor goes across all the rows for that sampling unit, then you have the most flexibility as to how you put them in the model and for which outcome. There's a lot of really bad advice out there for these sorts of models in the context of actor-partner data. So I'm trying to contradict that in part, because it is just a multivariate model when you boil down to it with some additional labeling describing what type of fixed slope you have. So in your homework, you will get a chance to practice this sort of data restructuring. And as per my usual, I don't expect you to ask the Google how to do it. You can just follow my example. So this is actually a more complex example than what you need. In the homework that's due next Wednesday, you only have 2 outcomes per person. So this would be 3. This is the code that I ran to create, come on, it's lagging, to change the data from wide to long here. So the way that this works is that the output statement writes a new line of data. So each time then it's going to write a new line and copy everything that was already on the line with it. So I have my categorical DV, which is just a string variable, so I'm cheating. Rather than making a numeric variable and adding labels, this is a faster way to do it. SAS doesn't care, because this is going to be just an identifier. Then I've got these are my outcome-specific intercepts. So I've got one for each in this pattern right here. And then marital is the name of the column that holds all three outcomes. Note that I have a different name here. So it starts out as example 5A wide, and I'm saving it as example 5A. For completeness, I could have called it 5A long or something to keep the labeling, but just that these are two different data sets because they're serving two different purposes. The original wide format is what we're going to use in the path models that go with these same data, whereas this one is the long format for today. And then data folks, your commands require that the outcomes have some kind of numeric suffix, so that I had to rename the 3 to make it work like that, and then the reshape command does all of that. Then it's up to you to create the outcome-specific intercepts. I set them to 0 initially and then turn them on if dv equals each case here. And then in R, I found a command called reshape, and it is fairly self-explanatory with respect to what's here as long as you have the titles of the arguments. Otherwise, it would be very hard to understand this code. But it wanted me to create a numeric version of dv, and so I changed it to a labeled version so that I could get the labels to show up on the output if I wanted them. And then here's the 3 dv-specific intercepts as well. And then last but not least, in the instance in which I'm treating dv as a factor variable, I changed the ref to be the dad because that's what it's going to be in SAS, and I wanted to match across programs. So I know we went over this last time, but it never hurts to repeat. Any questions on this syntax to reshape the data? Stack the data? Okay. Let me know if you do. So then I have 4 versions of the same model. Is this overkill? Probably. But I wanted to show you different strategies for how you can control what is given to you directly from the model so that you can adapt your problem to whichever strategy is going to be the most convenient and get you the closest to what you want to know straight out of the model. So the first 2 variants here, which I've labeled 0A and 0B, 0 because it's an empty model, why not, are going to keep the general intercept. So what we're going to get back is the intercept for the reference outcome, and then differences in the intercept for the other 2 outcomes. So dv here is used in SAS as an ID variable. It shows up right here. So it is structuring the R matrix. And in this example, we're sticking with just one kind. Do you remember what UN stands for?
Unstructured.
Unstructured. Unstructured means just let it be whatever it wants. So I'm sticking with a model in which each family member is going to have a separately estimated residual variance, and each pair is going to have a separately estimated residual covariance. So that's how I'm modeling the dependency. It's just letting it be whatever it needs to be. So in this case, because I want the intercept to represent the dad, to keep the output consistent across things, I'm putting in my 2 dummy-coded predictors here for whether it's kid and whether it's mom. So what I'm going to get directly is the intercept for dad, how the kid differs from dad, how the mom differs from dad. So I have a few other things that I might want to know. What is the intercept for each person is then a linear combination. So the intercept plus the dummy code for each person is how we get back to the intercept for each person. I might want to know differences between the non-reference groups, so kid versus mom, for instance. And I might want to know if there are differences across the 3 on average. So this is analogous to an omnibus main effect of condition, essentially. This is going to give me a 2 degree of freedom test as to whether there are any differences across dad, kid, and mom. I can do the same thing by using dv as a factor variable. So in this case, class in SAS is how you tell it, can you make those dummy codes for me? Cool, thanks. So all I have to do is write this here, and it takes the place of the individual dv dummy codes that I've specified. Notably, though, Now I have to refer to all three possibilities every time I reference the word DV, because internally it's expecting me to understand whether I'm talking about a 1 in each of the three potential columns or not. So you can do anything you want with these coding schemes as long as you know what they're doing internally. That's the tricky part. So these two are doing the same thing. The difference is whether or not I'm making the dummy codes manually or letting it do it for me as a factor variable. In Stata, very much the same. The only thing that's new here is this part. So Stata in mixed gives you a random intercept variance for the higher level sampling unit by default. I don't want that in this case. I want an unstructured R matrix instead. So that chunk right here, as it says in the comment, shuts it off. Once upon a time, Stata used to output standard deviations instead of variances. I don't know at what point they changed that, but just in case I'm running it on an older computer, I have the word variance here. I'm using residual maximum likelihood in both programs, and this is how in Stata you tell it that you want an unstructured R matrix by DV, and adding degrees of freedom. Here's my R matrix and R core matrix output, and then the lincoms do the same thing as the estimates, getting the model implied intercept for each person, as well as the difference between kids and moms as the alternative group, and then a test statement is how I do the omnibus group difference across the three different people. And annoyingly, this word small, Stata users, you have to type that on every single statement you write. You would think that because I asked it to use degrees of freedom up here, that would translate through the rest of the output. No. It wants to know for every single one, hey, do you want denominator degrees of freedom or no? So if I forget this, what I get back is a Z result, not a T. So you can get different p-values in smaller data sets with that. The second one here, IB last is changing the reference category to be the last one, so it matches the SAS output. Otherwise then, the how you refer to DV in Stata is with a number in front of it as to which internal dummy code you're talking about. So 1 is for kid, 2 is for mom, and 3 is for dad. Okay, any questions from the Stata users in the house? Well, now the grand finale, R. So I'm using GLS. That is the only way that I have found to estimate multivariate models that do not have random intercepts. All of the other mixed type things insist on putting them in there, and I don't want that. So the only difference with GLS, it's model instead of formula, otherwise it's structured the same way. This is using the general intercept. These two pieces right here are what give me my unstructured R matrix. So the correlation part, the way that it's estimated is that it directly estimates the correlations between the residuals, and then it can convert them into covariances once it has the variances. This weight statement is what gives me heterogeneous residual variances by outcome, or by DV in this case. You'll see the DV thing just because it's shorter to write. That stands for dependent variable, which means outcome, which means criterion. All of those words mean the same thing, but DV is just shorter. The output that we get from R is weird, and it took me a while to figure out what the numbers meant. And I was like, damn it, where's my R matrix? Like, oh, you can't have that. You get the multiplier, and you can have some correlations, and no, I want the R matrix. So I do what everyone does, ask my life partner how to get an R matrix out of GLS, and he helped me find a way to do it. So this function, get varcove and core matrix, respectively, gives you the R and the R core matrices that the other programs spit out. And it wants to know for whom. So this number is the number of the first case in the data set. So that's something that you would have to change to whatever case you want an R matrix for. It doesn't really matter in this case because the R matrix is assumed to be heterogeneous across families. But if you pick a family that has incomplete data, then your R matrix will be incomplete as well. And 3 dimensions. It's a 3 by 3 matrix in this case. So you would change that number to however many dimensions you have based on however many DVs you have. Then to get the rest of the output, that the tests, LINCOMs, estimates, etc., I have GLHT, and this is going to give me the omnibus test of whether there are any mean differences across my 3 outcomes. So it's lumping together the contrasts that differentiate kid from dad and mom from dad. And I had to tell it the degrees of freedom to get something that's approximately correct. This is easy in this case. It becomes a little bit more cumbersome as you get more complex models. It becomes decimals instead of whole numbers, but this works well enough here. And I got an interesting error message that it said, I couldn't have an F-test as I requested. It would only give me a chi-square. But then in the object it saved, the F was there. It just wouldn't show it to me. It's like, want to bet? So I asked to print the objects that were in there, and I actually got the right F-test. It just wouldn't give it to me. And people wonder why I hate R so much. Here are my GLHTs to get the remaining contrasts. So these are single degree of freedom. This is going to give me the predicted intercept for the kids. This is going to give me the predicted intercept for the moms. And the difference as well. Then the other way of doing it requires a lot less code. DV3 is what I'm using as my factor variable because that's the one in which the dad is the reference. And if it understands that these are levels of one variable and you might want to compare them, then you can do that more easily. With this command, emmeans, it asks for what you want pairwise comparisons across, and it also will do F-tests. It yelled at me about Satterthwaite as well for the right degrees of freedom, so I had to make it work. But anywho, so I realize that's a quick overview. Most of this code is going to be familiar to you, except maybe the factor part, because I've studiously avoided that. But any questions on the R code to this point? Okay, so both of these models up to this point are equal with respect to their model for the variance. So decisions about whether we make a general intercept or an outcome-specific intercept and how we set up the fixed effects, that is a completely separate set of decisions than how we structure the variance and covariance across outcomes. Now, it is possible that you could phrase it so that you have a variance for a reference outcome and a variance of the differences, but that would be a little bit less common of an application. So the R matrix that we end up with, so as printed, this is what it's called in SAS, and here's the correlation version of it. It tells you directly what the residual variance is for each outcome, and then what the residual covariance is across each pairs of outcomes, and then here's that covariance translated into a correlation that's bounded between -1 and 1 as usual. So it looks like the variability across family members, at least in the empty model, is relatively the same. So this might be a case where we could have, maybe we could test it, see if it needs to be the same or not, but the variability that we end up with after having predictors have their say may be different. So to be conservative to start with, I'm letting them stay different. Because it can't be wrong. The worst it can be is overly complicated. And here are the correlations between family members. So we would typically expect that outcomes from the same family are related, and to some extent they are. Although I noticed that that's column 1, that's going to be the kid with the mom is less related than the kid with the dad or the mom with the dad, which is maybe interesting, maybe not. Then SAS gives you this much, and I added the labels out here as to what they actually mean. So all of these numbers that are in the R matrix here are repeated in this form so that you can get a standard error. You can ignore the p-values for anything that's a variance because they're not valid. You can look at them for the covariances. UN means unstructured. So UN11 refers to column 1, row 1 of the R matrix right here. So this table and this table are redundant, except this table has a little more information to it. Information criteria table, this is where we're going to get our -2 log likelihood and a whole bunch of other fit statistics. And then I have the contrast table that is common across both analyses as to whether there are any differences across the 3 outcomes, and indeed there are. Yes?
When we have only one model, what kind of information we get from those fit statistics?
So this is residual maximum likelihood, which means that you cannot use -2 log likelihood to compare models that differ in fixed effects. So you cannot use likelihood ratio tests to talk about new predictors. The only thing that you would use it for is to make changes to the model for the variance. Like if you wanted to test a model where the residual variances were constrained equal and see if it fit worse, you could do that with the likelihood ratio test, keeping the same fixed effects in the model. But otherwise, we're not going to do much with it. It's just going to sit there. Practically speaking, in your homework, though, you'll enter that to make sure you have the right model, as usual. So this is what we're looking at right now is going to be common across all 4 model variants because they all have the same structure to their model for the variance. It's just unstructured. So it's a direct way of allowing dependency between the outcomes from the same family. You just tell SAS that there should be some, and it figures out how much there is. Stata folks, same is true for you. So it says residual unstructured, and then it lists the 3 residual variances, as well as the 3 residual covariances. So this part of the output looks a lot like SAS's output, except it's in a slightly different order, because SAS goes the order of the matrix, whereas Stata lists the order of variances then covariances. But then I also added, these are the tables that you get from adding W correlation as an option. So you can see your R matrix here and your R matrix in correlation form here. So there are several questions in your homework, like enter the residual variance from this model, enter the residual covariance. This is where you look for those answers. R core is variances and covariances. R is variances and covariances. R core is correlations. All right, and those of you who've been through longitudinal with me, yes, indeed, these are the same R matrices that they were then. These are R-only models, is what I would call them back in those days, as opposed to R plus G. Open up here. My little thing is hidden. Here we go. Now R. So here's what we get from R. The first thing I asked for was -2 times the log likelihood. So that's the number that you would enter into your homework for the first question, as per usual. Then it goes through and gives log likelihood. So that's in the bigger is better version. An incorrect AIC and BIC. So Stata has the same problem. When you're using residual maximum likelihood, AIC and BIC are not supposed to count the fixed effects. But they do in this case, and Stata does the same thing. So I'm not going to ask you anything about those because they differ across programs. Then you get this thing, which I was like, okay, this is the inside of the R correlation. So it's eliminating the redundant pieces of information and telling you what the residual correlation is between outcome 1 and 2, 1 and 3, 2 and 3. Okay, that's cool. Then we get to this thing. Variance function structure different standard deviations per stratum. Okay, so these are standard deviations, not variances. And then we end up with this. And when I first saw this, I was like, what the hell is that? I know the variance of the residuals for kid is not 1. It's some kind of weird multiplier that they estimate directly instead of the variance so that they can figure out what the variance is for each separate outcome as a function of this multiplier. And it's a multiplier of the standard deviation. Yes. And those of you who are like, what? Exactly. Like, can you just give me the variances? Is that so much to ask? So then again, here it is. So this is the output from getVarCov, which is the marginal variance covariance matrix. And so that means that this is put back together again in models that would have random effects, which this does not. So this is your R matrix. So this is the variance of the kid residuals. This is the variance of the mom residuals. This is the variance of the dad residuals. Here are the corresponding standard deviations, square root of those. And then here is core matrix, which is the actual R core. So this will be much more directly interpretable, just to look at these two and skip all of this part with the standard deviations and the multipliers. Then we get into GLHT. This is the F-test for whether there are any omnibus group differences across the outcomes. And it sent me this as a chi-square and said, you can't have your F. And so I said, yes, I can, because you already made it for me. Just need to print it. And so there is the F and the degrees of freedom that go with it. And the p-value. So I got all of the pieces that were missing. Okay. So that's the variance model output. Next up is the fixed effects. Questions before we do that? Yes?
Oh, maybe the fixed effects, because the estimates, I think it's in that first part where it said something like, I don't know, because we're treating some, or the fixed effects as like switches, like you were talking about before, but then it would give an estimate of like, I don't know, like for the homework I did like, is pancake 0 or 1, and it was like, the estimate was like 1.6. Like for the beta for that, that didn't make a whole lot of sense to me.
But it depends on how you set up the model,
Okay.
what it means. And so that's the part that we're getting into.
Okay.
Because, yeah, it's completely contextual, what it means. So here is the fixed effects output. It's the same in all the programs. So I just have it in SAS for convenience, and that way I only had to label it once. This part looks the same. The only difference is the degrees of freedom is printed in SAS and in Stata, and it's not printed in R because R doesn't do Satterthwaite degrees of freedom. So the model that I'm fitting is right here. This is the general intercept version. So I have then intercept as one of the rows here of my fixed effects solution, kid, and mom. So given that beta 0, 0 is a column of ones that applies to all three outcomes, then it is interpreted exactly like the way you learned how to interpret an intercept. It's the expected outcome when all predictors are 0. So when is this 0 and when is this 0? If we're talking about dad. So that's why this 1.9 is the mean attitudes on a scale of 1 to 4 for a dad. So then this effective kid operates just like a predictor dummy code would. So you can think of it as a predictor or you can think of it as a switch. It's a semantic distinction. This is a difference. So this is a slope that describes the change in attitude as you move from the 0 group to the 1 group. So as you go from dad to the kid's attitudes are less conservative by 0.3. So higher scores mean you're more conservative with respect to your gender roles, what women should be doing in the home, et cetera, et cetera. Likewise, this is how mom differs from dad as the reference. So if what you wanted to know are differences in attitudes between family member types, this gives you that directly. An alternative way of asking for the exact same model is to allow the common intercept, the general intercept, but then put in a categorical factor variable for DV. In SAS, the highest or last group is the reference, and you'll know that because it's the one that gets a 0 with dots. So that's who the intercept is for. Then we get the differences for kid and mom relative to that. So now I think you can probably tell why I went to the trouble to create a string variable here is because I wanted the labels attached to these things, not just 1, 2, 3. So then the linear combinations of the pieces of information that are not given include, okay, what is the intercept for kid? It's the intercept for dad minus the difference for kid gets me to what it is for kid. Likewise, the intercept for mom is what it is for dad minus the difference for mom gets to what it is for mom. And then the differences between the two non-reference outcomes is -1 for the kid and 1 for the mom gives me their difference right here. And I've written out the logic of what's happening out here as well to try and help keep track of this. If you let it do the factor variable thing, which is LS means in SAS or EM means in R and margins still, I think, in Stata, you end up with the mean per condition as part of your output under means and differences in means as well. So these two tables are generated with less effort if it understands it's a factor variable. So Nathan, then if you had a general intercept in your model, then your DV for your dummy code is going to be giving you the difference.
With the reference group.
The reference outcome, yep.
My brain just did not put that all together until now, so.
This is tricky. The homework that I gave you is functionally 4 cell means and a slope, and it is deceptively tricky.
Just like a lot to keep track of.
Yes, it is. But I'm going to give you some help as to how I set it up. Okay. Now here's the other way of doing it. We kick out the general intercept. This is what I did for your homework. So I started with this for section 1, and then I took it one step further for the addition of the training group as a predictor. So the big difference here is the introduction of no int in model. So it's in both of the SAS codes there. In Stata, I have no constant, which does the same thing. So note there's 2 different no constants in Stata because they serve 2 different purposes. The first one shuts off the fixed intercept. The second one shuts off the random intercept. And by the way, this 3-line thing is a line continuer to tell it to keep reading, which is necessary in older versions of Stata, but I figured out that you're allowed to treat it as a comment starter as well. So it's tricky. This took me a long time to not mess up, but look, there's 3 here, there's 3 here, there's 3 here, and there's only 2 here. So Stata is going to read this all as one idea, even though it's on separate lines, and then it will stop because this is not a continuer, it's just a comment. And these are all comments with just the 2. So no int, no int, no int. And as one does, I asked my life partner, how do I do this in R? And he said, you know where you write a 1? Make it a 0. Oh shit, that's the first thing that actually makes sense in R. 0 instead of 1. Cool, I can do that. And it worked. So that's the big difference. The rest of this is going to look similar, but it means different things. So now I have either all 3 dummy codes in the model or the categorical DV that's a factor variable. That means that what the model is going to give me directly is what is the mean for each kind of person. If I want to know any of the mean differences, I got to ask for those as linear combinations. So the 2 degree of freedom test is a linear combination of the difference between kid and mom and kid and dad. You just need to pick 2 out of the 3. The other 3 possible pairwise differences I've asked for here. If I have a factor variable, I have to do it a little bit differently by listing each of the values after this, but it's the same idea. In Stata, same thing. All 3 dummy codes go in. And you can also do that with just DV. And in the R code, the general intercept is shut off with the 0 here, and then all 3 dummy codes go in. And the rest of this looks relatively the same. The only difference is that if you tell it that you want a factor, then you can just refer to EM means to get all the means and mean differences. So save yourself a little bit of typing that way. But I wrote it all out anyway. So then here's what we get in this version. Here's my model. Every fixed effect is attached to one of the switches. So beta 0, 0 is only going to apply to create a predicted outcome if dad is 1. Beta 0, 1 is only going to kick in if kid is 1. Beta 0, 2 is only going to kick in if mom is 1. So what I end up with then is just the mean for each category, each type of person here. So I did that manually first, and then by using dv as a factor variable second. Here are the differences that I can then ask for, and then here are the means and mean differences that I get if I tell it that it's a factor variable. So model C of these four options is the one that I'm going to go with. The one where it looks like that, and I write out all three variables. Because I'm willing to do a little bit more typing to make sure I know what I have. So in your homework, let me pull up a Word document here. When I built your key, and yes, I do it in all three packages to make sure that it works and to make sure that I know what the solution should be. Like in SAS, it'd be like y model equals, and then I have like, your homework is looking at performance in making pancakes as one outcome and performance in making crepes as a different outcome. So my code looks like this, dvp and dvc. That directly gives me the mean for pancakes, the mean for crepes, if I do the no int like that. So in section 1, that's what I did. So I made each of these. If it's pancakes, then this is 1, otherwise it's 0. If it's crepes, then this is 1, otherwise it's 0. So then in the second part, I asked you to add the effects of training, because each person received training in either pancakes or crepes, but not both. So the idea would be their breakfast should improve for the type that was trained. If I gave you pancake training, you should be better at making pancakes. If I gave you crepe training, you should be better at making crepes. So there are multiple options on how to do this. No, it's like this, okay? So I'm skipping ahead to the predictor part. That way you can keep working on your homework. Now, if I do, let's say, training group, something, well, I'll just call that capital T for training, because I don't like typing. If I do this, what will happen? That T for the predictor, here, I'll make it a little bit, train, I'll call it that. That predictor will apply equally to both of these, because it's not attached to anything. So it's treated just like a regular predictor who controls every single line. If I want a separate effect of training for each outcome, what do I have to do? So if this is how I got a separate intercept for each outcome, how do I get a separate training slope for each outcome?
With an interaction term.
I need interaction terms, like that. Okay. Now this looks weird because there's no main effect of training. And that looks different than usually if you have an interaction term, then all the predictors have to have their slopes by themselves too. Not in this case. So this is directly going to tell me how the people who got one kind of training differ from people who got another kind of training when they're making pancakes. So you'd have to set it up as to who is the 0 and who is the 1. And this tells me the same training difference on people when they're making crepes. This is one option. This may make your head hurt, though.
I got an error message when I did that in R. Something about, I don't know, was having an issue that I think is that pancake and crepes were, the categorical were like completely opposite.
I'd have to see your code to see what the error is. I know that in R it's a colon, so I know that. But that, I mean, that's the only difference that I know of. So, like in this case, let's say that we set it up so that pancakes is the reference group and crepes are the alternative group. So the variable would be like this. So then to get to, say, what is, as an example, what is the mean for somebody who was trained in pancakes when they made pancakes? Well, in that case, it's just this. Because this would be the 0 group. This is shut off, this is shut off. If I wanted to know what is the mean for somebody when they made pancakes, when they were trained in crepes, then I have to add these two things together in a linear combination, like that. Now this is going to make your heads hurt, because some of the groups are linear combinations and some aren't. So you can do it this way, and it will work, but it may be harder than it needs to be. So let me show you what I did instead. My section 2 looks like this. So I have 4 terms here. I did the same trick with the switches, with the training group. So I made a dummy code that is 1 if they got pancake training and 0 otherwise. And I made a second dummy code that is 1 if they got crepe training and 0 otherwise. So now this term directly gives me people who got trained in pancakes when they made pancakes. This is people who got trained in pancakes but they made crepes. This is people who got trained in crepes, but they made pancakes. And this is people who got trained in crepes and made crepes. That's what I did. So then any questions about how these 4 groups differ from each other are linear combinations. But this is a cell of the design where you're crossing training and outcome type. And then in section 3, I added experience to each of these. So you would keep these in the model so that they would be the reference cell given experience equals 0, and then you can add 4 more interaction terms, which would look like 3-way interactions because you're adding the affected experience. That's what I did. Okay, questions? You can do it however you want. You can use factor variables, you can make up your own dummy codes, you can do whatever you feel like. I'm just telling you this is the way that I kept myself from going insane. This is also the strategy that I use anytime that I'm dealing with a design that is supposed to be fully crossed but isn't. So let's say that you have a study where people were supposed to do conditions A, B, and C, and in order to get the sample size you needed, you had to recruit 3 different cohorts of people. So you have cohort by condition. What if somebody from cohort 3 forgot to do condition C? Then you have a 3-by-3 table with a hole in it. And you can't fit the traditional main effects and interaction terms with the hole being there. But you can do something like this, where you literally create the cell mean out of dummy codes for each individual place, and then you can test whatever differences and interactions you feel like out of that. So this is what I mean by getting really good at linear models and being able to make them do your bidding. Because it's only a question of how much you want to fight with software, right? Some ways involve less fighting. All right, not due till Wednesday, so we can talk about this for 2 more classes, but I just wanted to give you some helpful hints as to how I approach the problem. Okay, 141. That means it's time to go very soon. Questions on this or example 5 before we call it a Tuesday? No? Good with this so far? Does this help explain the difference between general and DV-specific intercepts?
Yeah.
Yeah, I think in some cases shutting off the general intercept makes your life easier. Because then the model parameters are not all differences. They are means of various kinds, and you can get the differences as linear combinations. So. All right. Are we saturated? It's that time of semester, it's that time of day.
Yeah.
All right, well, happy garbage day, everyone. Thanks for being here. Thanks for sticking out, sticking in. What's the word? I'm mixing my metaphors. Hanging out, sticking with me. I'm out of prepositions. All right, then we'll call it a day. See you Thursday. Let me know if you need anything.